Hello all, today our topic is sharpening filter. We have already discussed in previous lecture about what is the sharpening filter, what are the types of sharpening filter in details. Now in this lecture we have discussed about using the second derivative for image sharpening, that is the Laplacian, and the first derivative also we have discussed. Then first using the second derivative for image sharpening, the Laplacian. The approach basically consists of defining a discrete formulation of the second order derivative and then constructing a filter mask based on that formulation. Isotropic filters are rotational invariant in the sense that rotating the image and then applying the filter gives the same result as applying the filter to the image first and then rotating the result. We are interested in the isotropic filters whose response is independent of the direction of the discontinuities in the image to which the filter is applied. In other words, isotropic filters are rotational invariant in the sense that rotating the image and then applying the filter gives the same result as applying the filter to the image first and then rotating the result. It can be shown that the simplest isotropic derivative operator in the Laplacian, which for a function image, that is f of x comma y of two variables, is defined as, that is, del square f is equal to delta square f upon del x square plus del square f upon del y square. Because the derivative of any order of linear operation, the Laplacian is the linear operator. To express this equation in discrete form, we use the definition keeping in mind that we have to carry a second variable. In x direction, we have del square f upon del x square, that is equal to f of x plus 1 comma y plus f of x minus 1 comma y minus 2 f of xy. Similarly, in the y direction, we have del square f upon del y square, f of x comma y plus 1 plus f of x comma y minus 1 minus 2 of f of xy. Therefore, it follows from the preceding three equations that the discrete Laplacian of a two variable is del square f of x comma y is equal to f of x plus 1 y comma y plus f of x minus 1 comma y plus f of x comma y plus 1 plus f of x comma y minus 1 minus 4 f of x comma y. The last equation can be implemented using the filter mask in figure A, which gives an isotropic result for rotations in increment of 90 degree. The mechanism of the implementation are as in for linear smoothing filters. We simplify are using the different coefficients here. The diagonal direction can be incorporated in the definition of the digital Laplacian by adding two more terms in above equation, one for each of two diagonal directions. The form of each new term in the same as either in equation 1 or 2, but the coordinates are along the diagonals because each diagonal term also contain a minus 2 f of x comma y term. The total subtracted from the difference term now would be minus 8 f of x comma y. Figure B shows the filter mask used to implement this new definition. These masks yields isotropic results in increments of 45 degree. You are likely to see in a practice the Laplacian masks in figures C and D. They are often from the definition of the second derivatives that are the negatives of the ones we use in equation, that is del square f upon del x square and del square y upon del y square. As such, they yield equivalent result, but the difference in sign must be kept in mind when combining, means by addition or subtraction, a Laplacian filter image with another image. Because the Laplacian is the derivative operator, its use highlights intensity, discontinuities in an image, and de-emphasizes region with a slowly varying intensity level. This will tend to produce images that have grayish edge lines and other discontinuities, all the superimposed on a dark featureless background. The background features can be recovered while still preserving the sharpening effect of the Laplacian simply by adding the Laplacian image to the original As noted in the previous topic, that it is important to keep in mind which definition of the Laplacian is used. If the definition is used has a negative center coefficient, then we subtract rather than add the Laplacian image to obtain a sharpened result. Thus, the basic way in which we use the Laplacian for the image sharpening is, that is, g of x comma y is equal to f of x comma y plus c of del square f of x comma y, where f of x comma y and g of x comma y are the input and sharp images respectively. The constant is c is equal to -1 if the Laplacian filter in figure A or B are used, and c is equal to 1 if either of the other two filters is used. This figure shows a slightly blurred image of the north pole of the moon, and figure B shows the result of filtering this image with the Laplacian marks in figure A. The last section of this image are black because the Laplacian contain both the positive and the negative values, and all the negative values are clipped at 0 by the display. A typical way to scale a Laplacian image is to add to its minimum value to bring the new minimum to the 0, and then scale and the result to the full 0, L-1 intensity range. The image in figure C was scaled in this manner. Note that the dominant features of the image are edges and sharp intensity discontinuities. The background, previously black, is now grey due to scaling. This greyish appearance is typical of Laplacian images that have been scaled properly. The figure D shows the result obtained using, with c is equal to -1, we are put in equation g of x comma y is equal to f of x comma y plus c del square f of x comma y in this equation. We are putting the value of c is equal to -1. The details in this image is unmistakably clearer and sharper than in the original image. Adding the original image to the Laplacian restored the overall intensity variations in the image, with the Laplacian increasing the contrast at the location of intensity discontinuities. The net result is an image in which the small details were enhanced and the background tonality was reasonably preserved. Finally, in figure E shows the result of repeating the preceding procedure with the filter in figure B. Here we note a significant improvement in sharpness over figure D. This is not unexpected because using the filter in figure B provides the additional differentiation, means sharpening in the diagonal directions. Results such as those in figures D and E have made the Laplacian a tool of choice for sharpening the digital images. This is all about this figure. Then our next topic is unsharp masking and high boost filtering, a process that has been used for many years by the printing and publishing industry to sharpen images consists of subtracting an unsharp version of an image from the original image. This process, called unsharp masking, consists of the following steps: blur the original image, subtract the blur image from the original, means the resulting the difference is called the mask, add the marks to the original. This figure figure A represent blur image of the north pole of the moon, while the figure B represent Laplacian without scaling, and C represent Laplacian with scaling, and D is image sharpened using the marks in figure A, and E is the result of using the marks in figure B. Letting, that is f bar of x comma y, denote the blurred image. Unsharp masking is expressed in equation form as follows. First we obtain the mass, that is g mass of x comma y is equal to f of x comma y minus f bar of x comma y. Then we add a weighted portion of the mass back to the original image, that is g of x comma y is equal to f of x comma y plus k into g mass of x comma y, where we include a weight, that is k. K is greater than equal to 0 for generality. When k is equal to 1, we have unsharp masking as defined above. When k is greater than 1, the process is referred to as high boost filtering. Choosing k is less than 1 de-emphasizes the contribution of the unsharp mask. Then this figure explains how the unsharp masking works. The intensity profile in figure A can be interpreted as a horizontal scan line through the vertical edge that transitions from the dark to light regions in an image, while the figure B shows the result of smoothing superimposed on the original signal, shown dashed for the reference, while the figure C is the unsharp mask, obtained by subtracting the blur signal from the original. By comparing this result with the section of figure C corresponding to the ramp in figure A, we know that the unsharp marks in figure C is very similar to what we would obtain using a second order derivative, while in figure D is the final sharpened result obtained by adding the marks to the original signal. The points at which a change of the slope in the intensity occurs in the signal are now emphasized, means sharpened. Observe that the negative values were added to the original. Thus, it is possible for the final result to have the negative intensities. If the original image has any zero values, or if the value of k is chosen large enough to emphasize the peaks of the marks to a level larger than the minimum value in the original, the negative values would cause a dark halo around edges, which if k is large enough can produce the objectionable results. Let us consider the example of image sharpening using the unsharp masking. This figure shows, the figure A shows a slightly blurred image of a white text on a dark grey background. Figure B was obtained using a Gaussian smoothing filter of size 5 by 5 with sigma is equal to 3, while the figure C is the unsharp marks, and figure D was obtained using unsharp masking with k is equal to 1. This image is slight improvement over the original, but we can do better. Figure E shows the result of using the equation g of x comma y is equal to f of x comma y plus k into g mask of x comma y, with k is equal to 4.5. The largest possible value we obtain, use and still keep positive all the values in the final result. The improvement in the image over the original image, original is significant. This is all about this. We are considering the example how the image sharpening using unsharp masking. This figure is represent this one. The next topic is using the first order derivative for image sharpening. It's called the gradient. First derivatives in image processing are implemented using the magnitude of the gradient for a function f of x comma y. The gradient of f at the coordinates x comma y is defined as the two-dimensional column vector. That is, del of f is equal to gradient of f is equal to matrix of g of x g by is equal to matrix of del of f upon del x del f upon del y. This vector has the important geometrical property that it points in the direction of the greatest rate of the change of f at a location x comma y. The magnitude, that is the length of a vector del f, is denoted by m of x comma y, where m of x comma y is equal to magnitude of del f is equal to under root of g of x square plus gy of square. is the value at x comma y of the rate of change of in the direction of the gradient vector. Note that m of x comma y is an image of the same size as the original, created when x and y are allowed to vary over all the pixels locations in F. It is a common practice to refer to this image as the gradient image or simply as the gradient when meaning is clear. Because the component of the gradient vector are derivatives, they are linear operators. However, the magnitude of this vector is not because of the squaring and the square root operations. On the other hand, the partial derivatives in equation del f is equal to grad of f is equal to matrix of gx comma gx upon gx gy and matrix of del f upon del x del f upon del y are not a rotational invariant isotropic, but the magnitude of all the gradient vector is. In some implementation, it is a more suitable computationally to approximate the square and the square root operation by the absolute values, that is m of x comma y is nearly equal to g of x, magnitude of g of x plus magnitude of g of y. This expression still preserves the relative changes in intensity, but the isotropic property is the lost in general. However, as in the case of the Laplacian, the isotropic properties of the discrete gradient defined in the following paragraph or in the following topic are preserved only for a limited number of rotational increments that depend on the filter marks used to approximate the derivative. As it turns out, the most popular marks used to approximate the gradient are isotropic at a multiples of 90 degree. These results are independent of whether we use the equation, that is m of x comma y is equal to magnitude of del f is equal to under root of gx square plus gy square, or using m of x comma y is nearly equal to magnitude of g of x plus magnitude of g of y. So nothing of significance is lost in using as later equation if we choose to do so. As in the case of the Laplacian, we now define the discrete approximation to the preceding equation and from this formulate the appropriate filter mark. In order to simplify the discussion that follows, we will use the notation in figure A to denote the intensity of image points in a 3x3 region. For example, the center point Z phi denotes f of x comma y at an arbitrary location x comma y, where z1 denotes f of x minus 1 comma y minus 1 and so on, using the notation introduced in figure as the simplest approximation to the first derivative that satisfy that condition stated in this section are gx is equal to z8 minus z5 and gy is equal to z6 minus z5. The two other definitions proposed by Roberts in the early development of digital image processing use cross difference gx is equal to z9 minus z5 and gy is equal to z8 minus z6. If we use the equation m of xy is equal to magnitude of del f is equal to under root of g of x square plus gy square and g of x is equal to z9 minus z5 and gy is equal to z8 minus zx, we are putting the value of gx and gy in this equation we get, that is m of x comma y is equal to z9 minus z5 square plus z8 minus z6 square raised to 1 by 2, means in square root. If we use the equations, that is m of xy is equal to magnitude of g of x plus magnitude of g of y and putting the value of g of x is equal to z9 minus z5 and gy is equal to z8 minus z6, we get that is m of xy is nearly equal to magnitude of z9 minus z5 plus magnitude of z8 minus z6, where it is understood that x and y varies over the dimensions of the image in the manner we described earlier. The partial derivatives terms needed in equation g of x is equal to Z9 minus Z5 and Gy is equal to Z8 minus Z6 can be implemented using the two linear filter marks in figure B and C. These marks are referred to as a Robert cross gradient operator. Marks of even sizes are awkward to implement because they do not have the center of symmetry. The smallest filter marks in which we are interested are of size 3 by 3. Approximation to Gx and Gy using a 3 by 3 neighborhood center on G5 are as follows. G of x is equal to del f upon del x is equal to Z7 in first bracket Z7 plus 2Z8 plus Z9 bracket complete minus in other bracket Z1 plus 2Z2 plus Z3, and Gy is equal to del f upon del y is equal to in first bracket Z3 plus 2Z6 plus Z9 bracket complete minus in other bracket Z1 plus 2Z4 plus Z7. These equations can be implemented using the marks in figure D and E. The difference between the third and the first row of the 3 by 3 image implemented by the marks in figure D approximate the partial derivative in the x direction, and the difference between the third and the first column in the other marks approximate the derivative in x direction. Why? Computing the partial derivative with these marks, we obtain the magnitude of the gradient as before. For example, we are substituting the value of Gx and Gy in equation m of xy is equal to magnitude of g of x minus magnitude of g of y. We get the value of m of x comma y is nearly equal to magnitude of in first bracket Z7 plus 2Z8 plus Z9 minus in other bracket Z1 plus 2Z2 plus Z3 magnitude plus magnitude of in first bracket Z3 plus 2Z6 plus Z9 minus in other bracket Z1 plus 2Z4 plus Z7. The marks in figure D and E are called Sobel operator. The idea behind using the weight value of 2 in the center coefficient is to achieve sum smoothing by giving more importance to the center point. Note that the coefficients in all the marks shown in figure is sums to 0, indicating that they would give a response of 0 in an area of constant intensity, as is expected of a derivative operator. As mentioned earlier, the computation of g of x and g of y are linear operations because they involve derivatives and therefore can be implemented as a sum of product using the special marks in figure. The nonlinear aspect of a sharpening with the gradient is the computation of m of x comma y involving the squaring and the square root, or the use of the absolute values, all of which are nonlinear operations. These operations are performed after the linear process that yields g of x and g of y. Let us consider the one example, that is the use of the gradient for the image enhancement. Let us consider the figure. The gradient is used frequently in industrial inspection, either to aid humans in the detection of defects or what is a more common as a pre-processing step in automated inspection. We will have more to say about. However, it will be instructive at this point to consider a simple example to show how the gradient can be used to enhance the defects and eliminate slowly changing the background features. In this example, enhancement is used as a pre-processing step for automated inspection rather than for human analysis. While the figure A shows an optical image of a contact lens illuminated by a lighting arrangement designed to highlight the imperfections such as the two edge defects in the lens boundary seen at 4 and 5 o'clock. The figure B shows the gradient obtained using the equation, that is m of x comma y is nearly equal to magnitude of g of x plus magnitude of g of y, with two Sobel marks in figure D and E. The edge defects also are quite visible in this image, but with the added advantage that a constant or slowly varying shades of a grey have been eliminated, thus simplifying considerably the computational tasks required for automated inspection. The gradient can be used also to highlight the small specks that may not be readily visible in a grayscale image. Specks like this can be foreign matter, air pockets in a supporting solution, or minuscule imperfections in this lens. The ability to enhance the small discontinuities in an otherwise flat gray field is the another important features of the gradient. This is all about this figure represent. Let us consider the another topics, or let us discuss about the another topic is combining the spatial enhancement method. With a few exceptions like combining the blurring with thresholding, we have focused attention thus for an individual approaches. Frequently, a given task will require application of several complementary techniques in order to achieve an acceptable result. In this section, we illustrate by means of an example how to combine the several of the approaches developed thus far to address a difficult image enhancement task. Let us consider the image is a nuclear whole body bone scan used to detect disease such as a bone infection and tumors. Our objective is to enhance this image by sharpening it and by bringing but out more of the skeleton detail. The narrow dynamic range of the intensity levels and high noise content make this image difficult to enhance. The strategy we will follow is to utilize the Laplacian to highlight the fine details and the gradient to enhance the prominent edges for reasons that will be explained shortly. A smooth version of the gradient image will be used to mask the Laplacian image. Finally, we will attempt to increase the dynamic range of the intensity levels by using an intensity transformations. The figure B shows the Laplacians of original image often using the filter. This image was scaled for a display only using the same technique as in figure C. We can obtain a sharp image at this point simply by adding figure A and B according to just by looking at the noise level in figure B. We would expect a rather noisy sharp image if we added figure A and B, a fact that is confirmed by the result in figure C. One way that comes immediately to mind to reduce the noise is to use a median filter. However, a median filtering is a non-linear process capable of removing image features. This is unacceptable in a medical image processing. An alternate approach is to use a mask form from a smooth version of the gradient of the original image. The motivation behind this is straightforward and is based on the properties of first and second order derivatives. The Laplacian, being a second order derivative operator, has the definite advantage that it is superior in enhancing the fine details. However, this causes it to produce noisier result than the gradient. The noise is most objectionable in smooth areas where it tends to be more visible. The gradient has a stronger average response in areas of significant intensity transitions, ramps and steps than does the Laplacian. The response of the gradient to noise and the fine detail is lower than the Laplacian and can be lower further by smoothing the gradient with an averaging the filter. The idea then is to smooth the gradient and multiply it by the Laplacian image. In this context, we may view the smooth gradient as a masked image. The product will preserve the details in the strong areas while reducing the noise in the relatively flat areas. This process can be interpreted roughly by combining the best features of the Laplacian and the gradient. The result is added to the original to obtain the final sharpened image. Figure D shows the Sobel gradient of the original image computed Component g, x and y were obtained using the marks in figure D and E respectively. As expected, edges are much more dominant in this image than in the Laplacian image. The smooth gradient image in E was obtained by using and averaging the filter of a size 5 by 5. The two gradient images were scaled for the display in the same manner as the Laplacian image, because the smallest possible value of a gradient image is 0. The background is black in the scale gradient images rather than the gray as in the scale Laplacian. The fact that the figure D and E are much brighter than figure B is again evidence that the gradient of an image with a significant edge content has a values that are higher in general than in Laplacian image. The product of the Laplacian and the smooth gradient image is shown in figure F. Note the dominance of the strong edges as a relative lack of visible noise, which is the key objective behind the masking and the Laplacian with the smooth gradient image. Adding the product image to the original result in the sharpened image shown in figure G. The significant increase in the sharpness of the details in this image over the original is evident in the most part of the image, including the ribs, spinal cords, pelvis and skull. This type of improvement would not have been possible by using the Laplacian or the gradient alone. The sharpening procedure just discussed does not affect in an appreciable way the dynamic range of the intensity level in an image. Thus, the final step in our enhancement task is to increase the dynamic range of sharpened image. As we discussed in some details, there are a number of intensity transformation functions that can be accomplished this objective. We do know from the results in the section that histogram equalization is not likely to work well on images that have the dark intensity distributions like our images have here. Histogram specifications could be a solution, but the dark characteristics of the image with which we are dealing lend themselves much better to a power law transformation. Since we wish to spread the intensity levels, the value of gamma has to be less than 1. After a few trials with this equation, we arrive as a result in figure H obtained with the gamma is equal to 0.5 and C is equal to 1. Comparing this image with a figure G, we see that significant new details invisible in figure H. The area around the wrist, hand, ankles and feet are good example of this. The skeleton bone structure also is much more pronounced, including the arm and leg bones. Note also the faint definition of the outline of the body and of body tissues, bringing out detail of this nature by expanding the dynamic range of the intensity level also enhance the noise, but figure H represent the significant visual improvement over the original image. The approach just discussed is representative of the types of processes that can be linked in order to achieve the results that are not possible with a single technique. The way in which the results are used depend on the application. The final user of the type of images shown in this example is likely to be a radiologist. For a number of reasons that are beyond the scope of our discussion, physicians are unlikely to rely on enhanced result to arrive at a diagnosis. However, enhanced images are quite useful in highlighting the detail that can serve as clues for further analysis in the original image or sequence of images. In other areas, the enhanced result may indeed be the final product. Examples are found in the printing industry, in image-based product inspection, in forensics, in microscopy, in surveillance, and in a host of other areas where the principal objective of enhancement is to obtain an image with a higher context of visual detail. This is all about the combining the spatial enhancement method, that is the Laplacian and the gradient image enhancement method. Thank you guys.